Welcome! In today's session, we will explore LeetCode problem number 104, maximum depth of binary tree. Together, we'll break down the problem, analyze its requirements, and discuss an efficient solution. Let's dive in. In this problem, we are tasked with finding the maximum depth of a binary tree. The maximum depth refers to the number of nodes along the longest path starting from the root node and going down to the farthest leaf node. A leaf node is a node that does not have any children. The input to the problem is the root of a binary tree, where each node is represented using a tree node structure. This structure includes three properties: val, which represents the value of the node; left, which points to the left child of the node or is null if there is no left child; and right, which points to the right child of the node or is null if there is no right child. The output is a single integer representing the maximum depth of the binary tree. Let's look at some examples to make this more concrete. In the first example, the input binary tree is represented as 3, 9, 20, null, null, 15, 7. When visualized, the tree structure looks like this. The root node has the value 3, with two children, 9 on the left and 20 on the right. The node 20 further has two children, 15 on the left and 7 on the right. To calculate the maximum depth, we consider the longest path from the root to any leaf. In this case, the longest paths are either 3-20-15 or 3-20-7, both of which consist of 3 nodes. Therefore, the maximum depth of this tree is 3. Now for the second example. The input binary tree is represented as 1, null, 2. When visualized, the root node has the value 1, and it has no left child but does have a right child with the value 2. The longest path from the root to a leaf is 1-2, which consists of 2 nodes. Thus, the maximum depth of this tree is 2. This example demonstrates how the solution should work even when the tree is unbalanced, with nodes only on one side. In the third example, the input is an empty tree, represented as. Since there are no nodes in the tree, there is no path from the root to a leaf. Therefore, the maximum depth in this case is 0. This highlights how the solution should handle edge cases where the tree is empty. Finally, let's discuss the constraints and edge cases for this problem. The number of nodes in the tree can range from 0 to 10,000, meaning the solution needs to handle very large trees efficiently. Each node's value is an integer, so we don't need to worry about other data types. For edge cases, if the tree is empty, the output must be 0. If the tree consists of only one node, the output should be 1. Additionally, the solution must handle unbalanced trees, whether all nodes are skewed to the left or the right, and still compute the correct depth efficiently. With these constraints in mind, the solution must be robust and scalable to handle all possible inputs within the given limits. To solve the problem of finding the maximum depth of a binary tree, we can think of the tree in terms of its recursive structure. Each tree consists of a root, and the depth of the tree is simply 1 plus the maximum depth of its left and right subtrees. This makes a recursive depth-first search, or DFS, a very natural approach. In this method, we calculate the depth of the left and right subtrees recursively and return the maximum of the two, plus 1 to account for the root node. The time complexity here is O(n), since we visit each node exactly once. The space complexity depends on the height of the tree, O(h), because of the recursive call stack. Although this approach is intuitive and straightforward, it does have a potential downside. For very deep trees, the recursion stack could grow too large, leading to a stack overflow. Another option is an iterative DFS approach, which avoids recursion by using a stack to simulate the traversal process. In this method, nodes and their depths are pushed onto a stack. As we process the stack, we update the maximum depth whenever we encounter nodes at deeper levels. The iterative DFS approach also has a time complexity of O(n), because each node is processed once. It uses O(h) space, where h is the height of the tree, since the stack is used to track the traversal path. While this approach avoids the risk of stack overflow, it can feel less intuitive and requires more verbose implementation compared to the recursive method. Another alternative is breadth-first search, or BFS, which processes nodes level by level using a queue. Here, the depth of the tree corresponds directly to the number of levels processed. To implement BFS, we initialize a queue with the root node at depth 1. For each level, we process all nodes in the queue, adding their children to the queue and incrementing the depth count. BFS also has a time complexity of O(n), as each node is visited exactly once, but its space complexity depends on the maximum width of the tree, O(w), which represents the highest number of nodes at any level. While BFS avoids recursion entirely and is particularly suited for level-by-level operations, it tends to use more memory in wide trees, as the queue can become large. For this problem, we've chosen the recursive DFS approach. It aligns naturally with the recursive nature of the problem, where the maximum depth is calculated by combining the depths of the left and right subtrees and adding one. This method is elegant and straightforward, making it particularly well suited for balanced or moderately sized trees. Recursive DFS maintains optimal time complexity at O(n), and for most real-world scenarios, the space complexity of O(h) is manageable, as trees are generally balanced. While iterative DFS and BFS can handle specific cases, such as extremely deep or wide trees, they introduce additional code complexity without offering significant performance advantages for the majority of test cases. Thus, recursive DFS strikes the right balance between simplicity and efficiency for this problem. There are trade-offs to consider when using recursive DFS. The most notable limitation is the risk of stack overflow in cases of highly unbalanced or very deep trees, where the depth may exceed 10,000. For these edge cases, an iterative approach, either DFS or BFS, provides a safer alternative, as it avoids the recursion stack entirely. On the other hand, BFS has higher space requirements in wide trees, since the queue must hold all nodes at each level. Ultimately, the final decision is to prioritize recursive DFS for its simplicity, readability, and efficiency in typical scenarios. However, when dealing with edge cases like extremely deep or unbalanced trees, iterative DFS offers a practical fallback to ensure robustness and avoid stack overflow issues. To determine the maximum depth of a binary tree, we aim to find the longest path from the root node to the farthest leaf node. The most efficient way to solve this is by using a recursive depth-first search, or DFS, which naturally aligns with the structure of binary trees. The idea is simple: the depth of a tree is 1, representing the root, plus the maximum depth of its left and right subtrees. For the base case, if the current node is null, we return a depth of 0 since we've reached beyond a leaf. For the recursive case, we calculate the maximum depths of the left and right subtrees by making recursive calls, and then we add 1 to account for the current node. This ensures we are always considering the longest path through the tree. Once all recursive calls complete, we return the result, which will represent the overall maximum depth of the binary tree. The pseudocode for this algorithm reflects the simplicity of the recursive approach. If the node is null, we return 0. Otherwise, we calculate the depth of the left and right subtrees recursively. Then, we take the maximum of these two depths and add 1 to account for the current node. This method employs a divide-and-conquer strategy, where the problem is broken into smaller subproblems for each subtree. The solution is highly efficient, with a time complexity of O(n), as each node is visited exactly once. It's also robust in handling edge cases, such as an empty tree, where the root is null and the depth is 0. This ensures the algorithm is optimal for all input scenarios. For example, if the tree consists of only one node, the root, the depth would be 1. Similarly, skewed trees, where all nodes are either on the left or right, are naturally handled by the recursion, as each recursive call processes one subtree at a time. The algorithm relies heavily on two data structures: the binary tree nodes themselves, which contain pointers to their left and right children, and the call stack, which manages the state of each recursive function call. Key operations include the recursive calls to compute subtree depths, the comparison of left and right depths to choose the maximum, and the addition of 1 to include the current node. While Python does not optimize for tail recursion, other languages might benefit from this optimization to reduce stack usage. Alternatively, an iterative approach using a stack or queue can handle cases where recursion depth might become a concern, such as with very deep trees. Let's walk through an example to see the algorithm in action. Consider a tree with the root node having a value of 3. From the root, the left subtree contains a single node with a value of 9, which has no children. Recursing into this subtree, we find that both children are null, so the depth is 0 plus 1, which equals 1. On the right subtree of the root, the node with value 20 has two children, 15 on the left and 7 on the right. Both of these nodes have no children, so their depths are 0 plus 1 is equal to 1. Combining these, the depth for the subtree rooted at 20 is max 1, 1, plus 1, which equals 2. Finally, at the root, the total depth is max 1, 2, plus 1, giving us a maximum depth of 3. Each recursive call evaluates a subtree and combines the results efficiently, ensuring that the algorithm traverses the entire tree in an optimal manner. This brings us to the complexity analysis. The time complexity is O(n), as every node is visited exactly once, and each node contributes a constant amount of work in terms of comparisons and additions. The space complexity is O(h), where h is the height of the tree, because the recursion stack stores the state of each active function call. For a balanced tree, the height is approximately log n, while for a skewed tree, the height can be as large as n. While recursion is elegant and efficient for most practical scenarios, it's important to understand these trade-offs, particularly the space usage associated with the stack. Overall, this recursive DFS solution remains one of the cleanest and most intuitive approaches for finding the maximum depth of a binary tree. This implementation solves the problem of finding the maximum depth of a binary tree using a recursive depth-first search (DFS) approach. Let's break it down. 1. TreeNode class. The TreeNode class represents a single node in the binary tree. Each node contains a value, val, and pointers to its left and right child nodes, left and right. 2. Solution class. The maxDepth function resides within the solution class. This function calculates the maximum depth of the binary tree. 3. Base case. The first if not root condition checks if the current node is none. If the node is none, it means we've reached the end of a path in the tree, so the function returns 0. For recursive calls, if the current node is not none, the function makes two recursive calls, one for the left subtree, self.maxDepth, root.left, and one for the right subtree, self.maxDepth, root.right. These calls calculate the maximum depth of the left and right subtrees starting from the current node. 5. Combine results. Once the depths of the left and right subtrees are returned, the function calculates the maximum depth of the current subtree by adding 1, for the current root node, to the maximum of the two depths, max, left_depth, right_depth. 6. Return statement. The result, representing the maximum depth of the entire binary tree, is returned to the caller. ###edge case is handled. If the input root is none, an empty tree, the function returns 0 immediately. The algorithm handles both balanced and unbalanced trees by recursively exploring the depths of all paths in the tree. ### complexity analysis. Time complexity, O(n), where n is the number of nodes in the tree. Each node is visited exactly once. Space complexity, O(h), where h is the height of the tree. This is the maximum depth of the recursion stack. This implementation is concise, efficient, and directly addresses the problem requirements by leveraging the recursive structure of binary trees. Here, we define the structure of a binary tree node using the TreeNode class. Each node has an integer value, and two child nodes, left and right, which represent the left and right subtrees respectively. We provide three constructors, one with no arguments for creating an empty node, one that initializes only the value, and another that initializes the value along with its left and right child nodes. Next, we move to the solution class, which contains our method for finding the maximum depth of a binary tree. The method, maxDepth, starts by handling the base case. If the root of the tree is null, meaning the tree is empty, we return a depth of 0. This ensures that we correctly handle trees with no nodes. If the tree is not empty, we proceed to calculate the depth of its subtrees recursively. We compute the depth of the left subtree by calling maxDepth on the root's left child, and similarly, we calculate the depth of the right subtree by calling maxDepth on the root's right child. These recursive calls allow us to traverse the tree down to its leaf nodes, calculating the depth at each level. Finally, we determine the depth of the current tree by adding 1 to the maximum depth of the left and right subtrees. The 1 accounts for the current node, which is the root of this subtree. By returning this value, we ensure that the depth of the entire binary tree is calculated correctly, all the way up to the initial root node. Here, we have a simple binary tree with a root, tree node, 3, and both left and right children. We begin by calling maxDepth, root, on the root node. The function makes a recursive call to explore the left subtree, starting with tree node 9. Since tree node 9 has no left or right children, we make recursive calls to maxDepth, tree node 9.left, and maxDepth, tree node 9.right. Both of these return 0 because the children are none. This means the depth of the subtree rooted at tree node 9 will be calculated as 1 plus max 0, 0, which equals 1. Next, we proceed to explore the right subtree of the root, starting with tree node 20. We now focus on the right subtree of the root. A recursive call is made to maxDepth, tree node 20, which leads us to its left child, tree node 15. Both left and right children of tree node 15 are none, so recursive calls to maxDepth, tree node 15.left, and maxDepth, tree node 15.right return 0. The depth at tree node 15 is then calculated as 1 plus max 0, 0 equals 1. Similarly, we process the right child of tree node 20, which is tree node 7. Since tree node 7 also has no children, recursive calls to tree node 7.left and tree node 7.right return 0. The depth at tree node 7 is computed as 1 plus max 0, 0 equals 1. With both left and right subtree depths for tree node 20 determined, we compute its depth as 1 plus max 1, 1 equals 2. Finally, we calculate the depth of the entire tree, starting with the root node, tree node 3. The left subtree depth, which we calculated earlier, is 1, and the right subtree depth, just computed, is 2. Using these values, the depth of the tree rooted at tree node 3 is determined as 1 plus max 1, 2 equals 3. This gives us the maximum depth of the binary tree for this example, which is 3. Next, we examine a different type of tree structure, a skew tree where all nodes are aligned to the left. In this example, the binary tree is skewed entirely to the left, meaning every node only has a left child. We start at the root, tree node 1, and call maxDepth, root. The function then makes a recursive call to explore the left child, tree node 2, and continues to the next left child, tree node 3. Since tree node 3 has no children, recursive calls to tree node 3.left and tree node 3.right return 0. The depth at tree node 3 is calculated as 1 plus max 0, 0 equals 1. Moving back up, the depth at tree node 2 is computed as 1 plus max 1, 0 equals 2. Finally, for the root node, tree node 1, the depth is calculated as 1 plus max 2, 0 equals 3. The maximum depth of this tree is therefore 3. In the final example, the input tree is empty, meaning the root is none. When we call maxDepth, none, the base case of the function immediately identifies that the tree is empty and returns 0. This is the maximum depth for an empty tree. With this, we've covered 3 scenarios: a balanced tree, a skew tree, and an empty tree, illustrating how the recursive solution handles each case effectively. The time complexity of the maxDepth function is O(n), where n is the total number of nodes in the binary tree. This is because the function uses recursion to traverse the entire tree, visiting each node exactly once. For every node, it computes the maximum depth of its left and right subtrees, which involves a constant amount of work like comparisons and arithmetic operations. As a result, the total work done is directly proportional to the number of nodes in the tree, leading to a time complexity of O(n). This is true regardless of the tree structure, whether it's balanced, skewed, or completely unbalanced, since every node must still be visited. Therefore, the time complexity remains O(n) in the best, average, and worst cases. Now, the space complexity of the maxDepth function is O(h), where h represents the height of the binary tree. This is because the function utilizes the recursion stack to keep track of active function calls. In the worst-case scenario, such as a completely unbalanced tree where all nodes form a single path, the recursion stack grows to the height of the tree, which is h. On the other hand, in the best-case scenario, such as a perfectly balanced tree, the height of the tree is log n, where n is the total number of nodes. Each recursive call consumes a constant amount of memory for local variables, and the recursion stack stores up to h function calls at a time. Therefore, the space complexity is O(h) in the worst case and O log n in the best case, depending on the tree's height. When comparing approaches, a brute force or naive method might involve manually traversing the tree level by level, keeping track of the depth explicitly. While this approach also has a time complexity of O(n), it requires additional memory for a queue or similar data structure to store nodes at each level of the tree. This could lead to a space complexity of O(n) in the worst case, especially if all nodes at one level are stored simultaneously in memory. The recursive approach, however, is more elegant and typically uses less memory. It avoids the overhead of maintaining a queue while still achieving the same O(n) time complexity. Mathematically, the recurrence relation for the recursive solution is T(n) equals 2T(n/2) plus O(1), which simplifies to O(n), since each node is visited exactly once. The space complexity, determined by the recursion stack, depends on the tree's height. For a balanced tree, the height is log n, resulting in O log n space. For an unbalanced tree, the height could be n, leading to O(n) space. In conclusion, the recursive solution is efficient, providing O(n) time complexity and O(h) space complexity for this problem. When solving this problem, it's important to avoid some common mistakes. First, there's often confusion between height and depth. Remember, this problem explicitly asks for the number of nodes along the longest path from the root to a leaf, which is essentially the height of the tree. Misinterpreting this can lead to off-by-one errors. Another frequent issue is forgetting to handle null nodes in recursive solutions. If you overlook the base case where the node is null, you might run into runtime errors, so always return 0 for null nodes. Inefficient implementation of DFS or BFS is another pitfall, especially in iterative solutions where managing the stack or queue incorrectly, like forgetting to include depth levels, can lead to infinite loops or incorrect results. Some may also overcomplicate the problem by trying to store depths of all nodes in extra data structures like arrays or hash maps, but this is unnecessary since the problem only asks for the maximum depth. Lastly, using global variables in recursive solutions might seem convenient, but it can introduce bugs, especially in concurrent environments or when running multiple test cases. Instead, rely on returning depth values directly from recursive calls for safer and cleaner code. In interviews, this problem is a great opportunity to demonstrate your understanding of the divide-and-conquer paradigm. You can explain how the problem breaks down into calculating the depths of the left and right subtrees, and then combining those results to get the maximum depth. It's also helpful to compare iterative and recursive approaches. While recursion is intuitive and elegant, it has a stack space complexity of O(h), where h is the height of the tree. For balanced trees or scenarios where stack overflow is a concern, iterative BFS or DFS is often better since it avoids recursion's overhead. Additionally, make sure to address edge cases during your explanation. These include an empty tree where the root is null, a single-node tree, or a highly skewed tree where all nodes are either on the left or right. Finally, reinforce your understanding of time and space complexity. Both recursive and iterative methods have a time complexity of O(n), where n is the number of nodes, as every node is visited exactly once. However, the space complexity can vary depending on the approach used. This problem also connects to several related problems that you might encounter. For example, LeetCode 111 asks for the minimum depth of a binary tree, which is similar to this problem but focuses on the shortest path to a leaf node. Another problem, LeetCode 543, involves calculating the diameter of a binary tree, which combines depth calculations with finding the longest path between any two nodes. LeetCode 226, which asks you to invert a binary tree, is another foundational problem that often uses similar recursive or iterative techniques. Finally, LeetCode 101 challenges you to determine if a binary tree is symmetric, reinforcing your understanding of tree traversal methods like DFS and BFS. When exploring alternative approaches, recursive DFS is a natural choice. It's concise and straightforward, but its trade-off is the O(h) stack space usage, which can lead to stack overflow for very unbalanced trees. Iterative DFS with a stack is another option, allowing you to explicitly manage the stack and avoid recursion, though it can be more verbose in implementation. Iterative BFS, which uses a queue, is another effective approach for this problem. One of its main advantages is that it processes nodes level by level, making it particularly intuitive for depth-related calculations. However, it's important to note its trade-offs as well. BFS requires additional memory to store the queue, and this can become significant for wide trees where many nodes need to be held in memory at the same level. Despite this, BFS often proves to be a practical and robust method for solving maximum depth problems, especially in balanced trees or when level order traversal aligns well with the problem's requirements. By understanding these trade-offs, you'll be prepared to choose the best approach based on the tree's structure and the constraints of the problem. Great job! Today, we tackled the maximum depth of binary tree problem, learned a practical solution using DFS, and reviewed key complexity metrics. Remember, recursive approaches are a cornerstone of tree traversal problems. Keep practicing, and don't forget to like and subscribe for more coding insights. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!